Welcome back to G Fun Facts Online, the show where we dive deep into the most fascinating stories from science, history, and beyond. I'm your host, and today we have a story that stretches across nearly 400 years. It's a tale about a mathematical puzzle so tricky, it stumped one of the greatest minds in history. But it's also a story about how a mystery from the 1600s was finally cracked open using the tools of modern physics, revealing a hidden connection between geometry and the quantum world. This isn't just about numbers and shapes. It's about a 380-year-old question posed by a philosopher to a princess and the incredible journey to find its answer. So how did a team of mathematicians in the 21st century finally solve a problem left unfinished by the legendary René Descartes? And what on earth does it have to do with Einstein's theory of relativity? Let's find out. Our story begins not in a modern university lab, but in the year 1643, through a series of letters. The correspondence was between two remarkable individuals: René Descartes, the French philosopher and mathematician who famously declared, "I think, therefore I am," and Princess Elisabeth of the Palatinate, a gifted intellectual in her own right. Descartes had recently revolutionized mathematics with his invention of Cartesian coordinates, the x and y axes we all learned about in school. He was at the peak of his intellectual powers. In one of his letters, he posed a geometric problem to the princess, something he believed he could solve to demonstrate his new methods. But, in a rare moment of fallibility, the initial problem proved to be too difficult, even for him. So, he did what any brilliant mind does when faced with an impossible task. He simplified it. And this simplified version gave birth to something truly beautiful and enduring, a concept now known as Descartes' circle theorem. Imagine you have three circles on a flat surface, and they are all touching each other. Think of three coins lying on a table, each one kissing the other two. Now you'll notice there's a small curved triangular space in the middle, and also a large space surrounding all three. The question is, could you find a fourth circle that fits perfectly into that central gap, touching all three of the original circles? And could you find another, much larger circle that encloses and touches all three? The answer is yes, and Descartes' theorem gives you the mathematical key to do it. The theorem describes the relationship between the sizes of any four circles that are all mutually tangent, or as they're poetically called, four kissing circles. To understand it, we need a simple concept called curvature. Curvature is just the reciprocal of a circle's radius. So, if a circle has a radius of 2 centimeters, its curvature is 1/2. If its radius is 10, its curvature is 1/10. A bigger radius means a smaller curvature, because the circle is less curved. A straight line can be thought of as a circle with an infinite radius, meaning its curvature is 0. Using this idea of curvature, Descartes' theorem is an elegant little equation. For four kissing circles with curvatures K1, K2, K3, and K4, the formula states that the square of the sum of all four curvatures is equal to 2 times the sum of their individual squares. So, if you know the curvatures of your first three circles, you can plug them into this formula and solve for the curvature and therefore the radius of that missing fourth circle. It's a stunning piece of 17th century mathematics. It works perfectly. But here's the catch. It only works for exactly 4 circles. This was just the simplified version of the problem. The grander, more profound question remained. What if you have more circles? What if you have 5 or 10 or 100 circles arranged in some intricate tangent pattern? Is there a universal law, a single equation, that describes the relationship between all of their sizes? This question, the natural extension of Descartes' work, sat there, unanswered. It tantalized mathematicians for generations. For over 380 years, it remained an open problem, a ghost from the past that no one could quite pin down. Until now. Fast forward to the present day, at Monash University in Australia. The long-awaited breakthrough has been unveiled by a team from the School of Mathematics, Associate Professor Daniel Matthews and his PhD candidate, Orion Zamaris. Published in the Journal of Geometry and Physics, their work finally provides the general equation that Descartes' successors had been searching for. They have extended the 17th century theorem to cover much larger, more complex arrangements of circles. To do this, they first had to define the patterns they were working with. They coined a wonderful term for them: n-flowers. An n-flower is a beautiful geometric pattern. Imagine a central circle, like the heart of a flower. Around it, you have a chain of n outer circles, which are the petals. Each petal circle is tangent to the central circle, and also tangent to its two neighbors in the chain. So a 3-flower would be a central circle with 3 petal circles around it, forming a closed loop. A 10-flower would have 10 petals. It was already known how to calculate the size of the central circle if you knew the sizes of all the outer petals. But what was missing was a single, explicit equation that related the curvatures of all the circles, the center, and all the petals in one go. That is what Matthews and Zamaris have now provided. They found the master equation, the general rule that governs these n-flowers no matter how many petals they have. It's a monumental extension of Descartes' original work, finally answering the question that had lingered for nearly 4 centuries. Solving an ancient problem like this is incredible on its own. But how they solved it is perhaps the most mind-bending part of this entire story. The solution didn't come from tinkering with compass and straight-edge geometry or traditional algebraic methods. The key came from a completely different and far more modern field of science: theoretical physics. The team employed a sophisticated and rather exotic mathematical tool called spinors. If you haven't heard of spinors, you're not alone. They aren't something you typically encounter in geometry class. Spinors are complex mathematical objects that are absolutely essential in quantum mechanics. They are used to describe the intrinsic angular momentum of elementary particles, like electrons, a property we call spin. But their usefulness doesn't stop there. Spinors are also a crucial component in Einstein's theory of general relativity, helping to describe the very fabric of spacetime. In fact, the specific type of spinors used by the Monash team were developed by the Nobel laureate Sir Roger Penrose and his colleague Wolfgang Rindler, specifically for their groundbreaking work on relativity. So what in the world are these high-powered tools from quantum physics and cosmology doing in a problem about circles on a flat plane? Orion Zamaris, the PhD student whose research was central to the breakthrough, noted just how surprising this connection was. He explained that their approach used advanced geometric tools inspired by physics. It turns out that the same mathematical structures that govern the strange, probabilistic world of quantum spin also provide the perfect language to understand how circles pack together. This is one of those beautiful moments in science that reveals a deep, underlying unity in the universe. Who would have thought that the rules describing an electron's behavior are mathematically related to the rules describing a drawing of kissing circles? It's a testament to the fact that mathematics is a universal language, and its principles echo across seemingly unrelated disciplines. The solution to a 380-year-old puzzle wasn't found by looking deeper into the old maps. It was found by bringing in a completely new kind of map, one drawn from the frontiers of modern physics. So what is the real significance of all this? Is solving a centuries-old math problem just a historical curiosity? A fun fact to share at a party? Well, yes, it's that, but it's so much more. This is a genuine advancement in the field of pure mathematics. It demonstrates the incredible power of modern mathematical techniques and the value of cross-disciplinary thinking. As Associate Professor Matthews said, "It's incredible to think that a question Descartes struggled with in the 1600s still has new answers waiting to be found." This discovery breathes new life into classical problems, showing that they can continue to inspire new ideas and lead to unexpected revelations. It also shines a bright light on the brilliant mathematical community at Monash University, and, in particular, on the exciting potential of young researchers like Orion Zamaris. It's worth noting that Zamaris is an alumnus of the John Monash Science School, a specialist secondary school, highlighting the importance of nurturing talent from a young age. He played a key role in making this historic achievement happen. Ultimately, this elegant solution to an ancient puzzle is a profound reminder of what the scientific endeavor is all about. It's a timeless journey of curiosity, where ideas from the past are not simply relics to be admired, but are active questions that can be illuminated by the powerful tools of the future. The story of Descartes circles, from a princess in 1643 to a PhD student in the 2020s, shows us a universe that is far more interconnected, intricate, and beautiful than we ever could have imagined. Thanks for tuning in to G Fun Facts Online. Join us next time as we explore another fascinating corner of our universe. Stay curious.